You were taught something in school that is not true, not approximately true, not a useful simplification, not one of those white lies that works fine until you reach graduate level physics and then quietly falls apart. Wrong. Measured, tested, confirmed wrong by the two most precise instruments ever pointed at the sky, built by two different space agencies on two different continents using completely different technology, and reproduced across 8 independent data releases over the course of 20 years. And the thing that is wrong is not some obscure footnote in a textbook you have forgotten. It is the single most important assumption in all of modern cosmology. The assumption on which every distance measurement, every dark energy calculation, every model of the universe's origin and fate depends. The assumption that the universe has no preferred direction. You were told there is nothing special about where you are or which way you are facing. That the cosmos looks statistically the same in every direction. That there is no center, no edge, no axis, no orientation to reality. This is the cosmological principle, and it has been treated as something close to sacred since Einstein needed it to solve his field equations in 1915. Every popular science documentary repeats it. Every physics classroom teaches it. Every textbook prints it as settled fact. In 2003, NASA finished building the most detailed map ever made of the oldest light in the universe. And in that map, at the very largest scales, there was a direction, a single preferred axis, threading through the oldest signal in existence, around which the largest patterns in the cosmos organize themselves in a way that the standard model says should be impossible. And when the axis was measured, when its orientation was calculated and plotted against the sky, it pointed with disturbing precision toward the plane of Earth's orbit around the Sun, a plane defined by the gravitational dynamics of a protostellar disk that collapsed 4.6 billion years ago around an unremarkable star in an unremarkable arm of an unremarkable galaxy. The signal it aligned with was emitted 9.2 billion years before our solar system existed. Two physicists at Imperial College London gave it a name in 2005. They called it the axis of evil, and the data behind that name has now been confirmed at greater than 99.9% confidence. That is not a marginal hint. That is not a suggestive signal buried in noise. In particle physics, that level of significance would trigger a Nobel Committee. In cosmology, it has triggered 20 years of silence. Here is what the axis of evil actually is, in concrete terms, because the name gets thrown around and the details usually get lost. The cosmic microwave background, the CMB, is not just old light, it is the oldest light, released 380,000 years after the Big Bang, when the universe finally cooled enough for hydrogen atoms to form and photons to travel without being scattered by free electrons. Before that moment, the universe was a dense, opaque plasma, every photon bouncing off every charged particle, light unable to move more than a short distance in any direction. After that moment, the universe became transparent. Light could travel freely, and the light that was released at that instant has been traveling ever since, stretching and cooling as space expanded. Until today, it arrives at our instruments as faint microwave radiation at a temperature of 2.7255 Kelvin, roughly 2.7 degrees above absolute zero, coming from every direction in the sky, nearly uniform, the fading afterglow of the moment the universe first became visible to itself. Nearly uniform, not perfectly uniform. There are fluctuations, temperature differences of about 18 microkelvin, 1 part in 100,000, varying from point to point across the sky. Those fluctuations are the seeds of everything. Every galaxy, every star, every planet you have ever seen in a photograph, every atom in your body traces back to a region in the primordial plasma that was marginally denser or less dense than its neighbors 380,000 years after the beginning. Map those fluctuations, and you are looking at the architectural blueprint of the universe, the original plan from which all of cosmic structure was built. To analyze these fluctuations, physicists decompose them into spherical harmonics, which are essentially the vibrational modes of a sphere. Think of it like sound. A drum vibrates in patterns, some with long wavelengths spanning the whole drumhead, some with short wavelengths, creating fine detail. The CMB sky vibrates the same way, except the drum is the entire observable universe, and the vibrations are temperature differences. Each mode is labeled by a number called L. Low L values correspond to the largest patterns, structures that stretch across most of the sky. High L values correspond to fine detail, tiny hot and cold spots separated by fractions of a degree. The L equals 1 mode, the dipole, is the simplest pattern. One half of the sky slightly hotter, the other slightly cooler. It is dominated by our own motion through the CMB rest frame. We are moving at about 369 kilometers per second toward the constellation Leo, and that motion Doppler shifts the CMB, making it hotter ahead of us and cooler behind. The dipole tells us about us, not about the early universe. The first cosmologically interesting modes are L equals 2, the quadrupole, and L equals 3, the octupole. These are the big ones. They span angular scales of 90 degrees and 60 degrees on the sky. They represent the very largest structures in the primordial universe, patterns so enormous they stretch across a significant fraction of the observable cosmos. And according to everything we think we know about inflation and the standard cosmological model, they should be random. Their orientations should bear no relationship to each other, no relationship to the dipole, and absolutely no relationship to the orbital mechanics of a star system that would not exist for another 9 billion years. Max Tegmark saw it first. Swedish-born, based at the University of Pennsylvania at the time, Tegmark had built a reputation for extracting clean cosmological signals from messy datasets. In February 2003, within days of NASA releasing the first year of WMAP satellite data, Tegmark and his colleagues Angelica de Oliveira Costa and Andrew Hamilton published a foreground cleaned map of the CMB that revealed something the official NASA maps had obscured in their processing. The quadrupole and the octupole shared an axis. Both modes had their temperature variations concentrated in a plane, and that plane was roughly the same for both of them, pointing toward the constellation Virgo at galactic coordinates of approximately 260 degrees longitude, 60 degrees latitude. Their follow-up paper in July of that year put numbers to the alignment. The probability of this occurring by chance was about 1 in 60. 1 in 60 is notable. It is not devastating, but then 4 physicists turned notable into devastating. Craig Copey at Case Western Reserve University, Dragan Huterer at the University of Michigan, Dominic Schwartz at the University of Bielefeld in Germany, Glenn Starkman, a distinguished university professor and Guggenheim Fellow, also at Case Western. In March 2004, they submitted a paper that did something nobody had done carefully before. They checked the orientation of the quadrupole and octopole not just against each other, but against known features of the local environment. The CMB dipole direction, the plane of the ecliptic, the direction of the equinoxes. What they found was, in the literal meaning of the word, incredible. The quadrupole and octopole were aligned with each other at 99.97% confidence. 3 of the 4 planes defined by the multipole vectors were perpendicular to the ecliptic plane at 99.8% confidence. The normals to these planes aligned with both the CMB dipole direction and the direction of the equinoxes at 99.9% confidence. The ecliptic, the plane traced out by Earth's yearly orbit around the Sun, threaded precisely between the hot and cold regions of the CMB across roughly a third of the sky. Think about what that means for a second. The ecliptic is a local feature. It is defined by angular momentum conservation in a collapsing cloud of gas and dust 4.5 billion years ago. It has nothing to do with cosmology. There is no known physics, no force, no field, no interaction of any kind that connects the orbital plane of 8 planets around one star to the temperature pattern of radiation emitted 9.2 billion years before that star ignited. The 2 things exist on opposite ends of the cosmic timeline. They operate at opposite ends of the physical scale, and they line up. Kate Land was a doctoral student at Imperial College London when she and her supervisor, Joao Magueijo, generalized these findings. Their paper, submitted in February 2005, republished in Physical Review Letters, showed the alignment extended from L equals 2 all the way through L equals 5, projecting statistical isotropy at greater than 99.9% confidence across multiple multipole moments. They called the preferred axis the axis of evil. The name was borrowed from George W. Bush's 2002 State of the Union address, a deliberate provocation by Magueijo, who understood that a sticky name is a weapon against institutional forgetting. Once something is named, it is harder to pretend it does not exist. The combined a priori probability of all the observed alignments occurring by chance is less than 1 in 12,000. Some analyses put it closer to 1 in 24,000. And if the alignment is real, if it is not a systematic error and not a statistical fluke, then the largest structures in the observable universe may be shadows of something even larger, something that was there before the universe, as we understand it, began, something encoded in the initial conditions of reality that has persisted through 14 billion years of expansion and cooling, visible only in the faintest, oldest light there is. You would not fully appreciate what that means yet, but remember it, because this is where the whole thing ends up. Land and Magueijo's paper left exactly 3 options on the table, and all 3 are unacceptable. Option 1. The universe genuinely has a preferred direction that correlates with the orbital plane of our solar system, which would overturn the Copernican revolution and place Earth in a structurally privileged position in the cosmos. Option 2. There is an unknown systematic error affecting 2 completely independent space missions designed by different teams using different technology. An error so subtle it has survived 20 years of scrutiny by the best instrumentalists alive. Option 3. This is a statistical coincidence with a probability of less than 0.008%. None of those lets you sleep well. And the reason none of them has been resolved is not that physicists have not tried. It is that the anomaly refuses to cooperate with any explanation anyone has proposed. But that is not even the part that should unsettle you, because the axis of evil is not a single anomaly. It is the most famous member of a family of anomalies that, taken together, suggests something is wrong with the way we understand the universe at its very largest scales. And to understand why the family matters more than any individual member, you need to understand the thing it threatens. Because the thing it threatens is not just a theory, it is the floor the entire field is standing on. The cosmological principle says that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. It does not claim the universe is perfectly uniform. Galaxies exist. Galaxy clusters exist. The cosmic web exists, with filaments and walls and voids stretching across hundreds of millions of light years. But it claims that if you zoom out far enough, if you average over volumes large enough, all that structure washes out and what remains is smooth, featureless, directionless, a universe without a center, without an edge, without any axis or orientation that would distinguish one direction from another. This is not an observation, it is an assumption. And it is an assumption that carries the weight of the entire mathematical framework of modern cosmology on its back. Einstein needed it in 1915 because, without homogeneity and isotropy, his field equations for the large-scale universe become intractably complex. There are too many degrees of freedom, too many possible configurations of matter and geometry. The cosmological principle collapses all that complexity into a single elegant metric. Edward Arthur Milne formalized the principle and gave it its name in the 1930s. Alexander Friedmann had already used it in 1922 to derive the equations that describe how the universe expands. Georges Lemaitre used it independently in 1927. Howard Robertson and Arthur Walker completed the mathematical framework in the 30s. The result is the Friedmann-Lemaitre-Robertson-Walker metric, the FLRWD metric, which describes a universe that is homogeneous and isotropic and expanding. It is the mathematical backbone of the lambda CDM model, the concordance cosmology, the standard model of the universe that is printed in every textbook and assumed in every paper and taught in every graduate course on the planet. And here is what makes the cosmological principle so dangerous to question. It is not a peripheral assumption. It is load-bearing. The evidence for dark energy depends on it. The accelerating expansion of the universe, discovered in 1998 by two independent teams studying Type Ia supernovae. The discovery that won Saul Perlmutter, Brian Schmidt, and Adam Ries the 2011 Nobel Prize relies on distance measurements calibrated against an isotropic, homogeneous background. If the universe is not isotropic, those distance measurements change. The evidence for dark matter, the age of the universe, the geometry of space, the ratio of baryonic matter to total matter, all of it passes through the FLRW metric. All of it depends on the cosmological principle being true. If the principle fails, the entire concordance model does not just need adjustment. It needs to be rebuilt from the foundations. And nobody in cosmology wants to rebuild the foundations. Not when they have spent 30 years constructing precision measurements on top of them. Inflation was supposed to make this a non-issue. Alan Guth's 1981 proposal that the universe underwent a brief period of exponential expansion in its first fraction of a second, doubling in size at least 60 times in roughly 10 to the minus 32 seconds, was partly motivated by the need to explain the observed isotropy of the CMB. If the universe expanded by a factor of at least 10 to the 26 during inflation, any pre-existing anisotropy, any preferred directions, any inhomogeneities in the initial conditions would be stretched so far beyond the observable horizon that we could never detect them. Inflation predicts isotropy. The near-perfect uniformity of the CMB at small angular scales is inflation's single greatest observational triumph. So if the CMB has real, confirmed, persistent, preferred directions at its largest angular scales, then inflation either did not happen the way we think it did not last long enough to stretch away all primordial anisotropity, or the pre-inflationary universe had even more structured initial conditions than anyone has proposed. And that third option, the one that requires structured initial conditions, is the one that nobody wants to think about, because it asks the question that inflation was specifically designed to avoid. What came before? And here is the part where the individual anomaly becomes a pattern, and the pattern becomes something harder to dismiss. The axis of evil, the alignment of the quadrupole and octopole, is the anomaly that got a name. But it is not alone. The quadrupole is not just strangely oriented, it is also too weak. The measured quadrupole power is roughly 2/3 of what the lambda CDM model predicts, with odds of about 1 in 20 of being that low by chance. On its own, 1 in 20 is nothing to panic about. But the quadrupole is not on its own. The two-point angular correlation function, the most fundamental statistical measure of the CMB, which tells you how temperatures at different points on the sky relate to each other, is essentially zero for angular separations greater than about 60 degrees. The standard model predicts significant correlations at these scales. The data shows virtually none. Copy, Couturer, Schwartz, and Starkman demonstrated that only about 0.03% of simulated lambda CDM universes produce correlations this low. That is a 3.5 sigma departure from the model. The largest scale patterns in the CMB are not correlating with each other the way they should. Then there is the parity asymmetry. Decompose the CMB into even multipoles. L equals 2, 4, 6, and odd multipoles L equals 3, 5, 7. In the standard model, there is no reason for one parity to dominate the other. In the data, odd multipoles carry significantly more power than even multipoles at low L. The asymmetry has p-values of 0.2 to 0.4%, depending on the analysis. It is there in WMAP. It is there in Planck. It persists. And the hemispherical power asymmetry. Divide the sky into two hemispheres along a particular axis. One hemisphere has noticeably more fluctuation power than the other. The asymmetry axis sits near galactic coordinates of about 246 degrees longitude, minus 2 degrees latitude, close to the ecliptic, and it persists to multipoles as high as L equals 600, well into the range where individual anomalies should have been washed out by the sheer number of independent modes. The significance is approximately 3 sigma. Each of these anomalies, taken individually, is a 2 to 3 sigma fluctuation. Not one of them, by itself, would justify a major revision of the standard model, but they are not individual. They do not affect random unrelated parts of the CMB. They all occur at the same angular scales, the very largest. They all involve the lowest multipoles, and they all cluster around related preferred directions near the ecliptic and the CMB dipole. The pattern is coherent, and the probability of this coherence arising by chance is enormously smaller than the probability of any single anomaly. This is the thing that the press release version of the CMB systematically omits. At small angular scales, L above about 30 or so, the CMB power spectrum matches lambda CDM predictions with breathtaking precision. The acoustic peaks, the positions of bumps and dips in the power spectrum that encode the physics of sound waves in the primordial plasma, are fit by the model to within a fraction of a percent. This is the CMB that gets the headlines, the CMB of precision cosmology, the one that makes cosmologists say, we live in a golden age. But at the largest scales, below L equals 5 or so, the picture is different. The modes that span the entire sky, the ones that carry the deepest information about the geometry and topology of the universe, are anomalous. They are too weak, too aligned, too correlated with each other and with the local environment, and too asymmetric between parities. The success story is the small-scale story. The large-scale story is the one nobody puts in the press release. And the reasonable hope, the scientifically justified hope, was that all of this was a WMAP problem. That when a better instrument came along, the anomalies would disappear. That they were artifacts of some subtle systematic in WMAP's differential radiometers, or residual contamination from galactic foregrounds that the WMAP team had not fully subtracted, or a statistical fluke amplified by WMAP's particular sky scanning strategy. This was not wishful thinking. It was a legitimate scientific expectation. Anomalies in a first-generation dataset frequently vanish when a second-generation dataset with superior sensitivity comes along. The second-generation dataset was called Planck, and it changed everything by changing nothing. Planck was the European Space Agency's flagship CMB mission, approved in 1996, launched in May 2009. It was designed from the ground up to surpass WMPS in every measurable way, where WMAP observed in 5 frequency bands, Planck observed in 9, giving it vastly superior ability to separate the primordial CMB signal from galactic foreground contamination. Where WMAP's angular resolution was about 13 arc-minutes at its best, Planck achieved 5 arc-minutes, resolving 3 times finer detail. Where WMAP used differential radiometers that measured temperature differences between 2 points on the sky, Planck used 2 completely different detector technologies: high electron mobility transistor radiometers in its low-frequency instrument and spiderweb bolometers cooled to 1/10 of a degree above absolute zero in its high-frequency instrument. If WMAP had a systematic error that produced the anomalies, there was no reason Planck should reproduce it. The instruments were different. The scanning strategy was different. The orbits were similar, both at the Sun-Earth L2 Lagrange point, but the way each satellite sampled the sky was not. The foreground subtraction pipelines were different. The data analysis teams were different. Everything was different, except the sky itself. In March 2013, the Planck collaboration released its first cosmological results. 30 papers covering everything from the power spectrum to gravitational lensing to the cosmic infrared background. Paper number 23 was titled Isotropy and Statistics of the CMB. It ran through the full catalogue of known anomalies, one by one. The quadrupole-octopole alignment, the low quadrupole power, the lack of large angle correlations, the hemispherical asymmetry, the parity asymmetry. For each anomaly, 4 independent component separation algorithms, Commander-Ruler, NILC, SEVIM, and SMICA, each using fundamentally different mathematical approaches to stripping away galactic emission, produced consistent results. The conclusion, stated with the measured understatement characteristic of large scientific collaborations, was that the anomalies previously observed in the WMAP data were now confirmed at similar levels of significance, about 3 sigma, confirmed by a completely independent instrument, using completely different technology, analyzed by a different team, with 4 different foreground cleaning algorithms, all agreeing the anomalies were not in WMAP's radiometers. They were not in the foreground subtraction. They were in the sky. The 2015 Planck release reinforced the findings with improved data processing. The 2018 legacy release, Planck's final word, its definitive dataset, reconfirmed them. There was no escape route. The hope that Planck would kill the axis of evil died in 2013. What Planck actually did was upgrade it from a suspicious anomaly to a confirmed feature of the observable universe. Dominic Schwartz, the Bielefeld physicist who had been tracking these anomalies since the original WMAP detection, captured the mood in an interview that is as close to a confession as cosmology gets. For a long time, he said, part of the community was hoping that this would go away, but it has not. Hoping it would go away. That is an extraordinary thing for a scientist to say about data. You do not hope data goes away. You explain it, or you revise your model to account for it. But the axis of evil sat in a space where neither option was available, where no explanation worked and no model revision was palatable. And so the community's dominant response was to hope. The definitive cross-mission comparison came in 2015, when Coppi, Hutterer, Schwartz, and Starkman published a paper analyzing WMAP's 7-year and 9-year data releases alongside 3 Planck foreground cleaned maps simultaneously. They were looking for exactly one thing. Did the anomalies survive the transition between missions? The answer was unambiguous. The quadrupole-octopole alignment persisted at 95 to 99.9% confidence across every single map, the strongest alignment between the combined multipole planes and the CMB dipole direction, registered at 99.6% confidence or higher. The angular separation between the quadrupole and octopole preferred planes was a mere 9 to 13 degrees in every dataset. As Glenn Starkman pointed out, if you had made a systematic error with WMAP, you would not expect Planck to reproduce it. The instruments have nothing in common except the universe they are looking at. And the quartet kept going. They had been the anomaly's most persistent investigators for over a decade by that point, publishing the landmark papers, performing the cross-checks, writing the reviews that kept the data in the scientific conversation when the broader community seemed content to look away. Schwartz had trained at TU Wien and CERN. Hutterer wrote accessible articles trying to bring the anomaly to public awareness, including a 2007 piece for Astronomy magazine titled, "Why is the Solar System cosmically aligned. Starkman's credentials, the Distinguished University Professor title, the Guggenheim Fellowship, made dismissal more difficult. When someone of that stature tells you the data is anomalous, the usual response of questioning the analyst's competence does not work as well. Then, in 2025, came the most comprehensive analysis yet. Patel, Alluri, and Ralston published a paper in Monthly Notices of the Royal Astronomical Society, volume 539, that examined all 8 publicly available full-sky CMB maps from WMAP's first-year release through Planck's legacy dataset. Every map, every release, every foreground cleaning algorithm. Their conclusion was stated without hedging. The anomalous alignments among multipoles L equals 1, 2, and 3 are very consistent and robust across every data release. The first 60 cosmological modes of the CMB are intrinsically anisotropic at greater than 95% confidence in all datasets. Not some datasets, all datasets. Not with some algorithms, with all algorithms. Not in one mission's data. In both missions' data, over 20 years, 8 releases. The anomaly does not fluctuate. It does not drift. It sits in the data like a fingerprint, identical in every photograph, waiting for someone to explain who left it there. And these largest modes, L equals 2 and 3 and 4, the ones that are anomalous, are not just any modes. They are the modes that span the entire observable universe. They are sensitive to the global properties of the cosmos, its overall geometry, its topology, its boundary conditions, in a way that smaller modes are not. If the universe has a shape, if space is finite, if there is a topology connecting distant regions, the signatures would appear here, at these scales, in these modes. They are the only vibrations large enough to feel the edges of reality, if reality has edges. That thought should sit with you for a moment, because what it means is that the anomalies everyone has been trying to dismiss for 20 years might not be noise at all. They might be signal, the deepest signal in the dataset, the one that carries information not about the contents of the universe, but about the container, about the shape of the thing we are inside of. But before we get to the explanations and to why all of them fail, there is a human story running underneath the data that tells you something the papers never will. Because the axis of evil is not just a measurement, it is a test of what happens when a scientific community encounters evidence it does not want. Joao Magueijo is the kind of physicist who makes other physicists uncomfortable. Born in 1967 in Évora, Portugal, he arrived at Imperial College in the 90s and immediately started picking fights with the establishment. His 1998 varying speed of light theory proposed that the speed of light was not constant in the early universe, that it may have been up to 60 orders of magnitude faster in the first moments after the Big Bang, offering an alternative to inflation that solved the horizon problem without exponential expansion. The response from mainstream cosmology ranged from skepticism to outright hostility. His 2003 book, Faster Than the Speed of Light, reads as part physics monograph and part war diary, documenting his battles with what he perceived as a field hostile to genuinely new ideas. He holds the same research fellowship at St. John's College, Cambridge, once held by Paul Dirac and Abdus Salam, two of the greatest theoretical physicists of the 20th century. The name axis of evil was pure Magueijo, borrowed from geopolitics, designed to stick in the memory chosen because he understood that a provocative name is a form of insurance against institutional amnesia. You can quietly shelve an anomaly. You cannot quietly shelve an anomaly that has been given a name the public remembers. Kate Land was his doctoral student. She grew up in Sussex, studied mathematics and astrophysics at Cambridge, and came to Imperial for her PhD. The Axis of Evil paper was part of her thesis work. She described Magueijo as not only a genius, but a lot of fun to work with, very supportive, unpatronizing, and encouraging. After finishing her doctorate, she moved to Oxford as a postdoctoral researcher, where she co-founded Galaxy Zoo, the citizen science platform that crowdsourced the classification of millions of galaxies using human pattern recognition at a scale no research team could match alone. Galaxy Zoo was partly inspired by the Axis of Evil work. Land wanted to investigate claims about alignments in the rotational directions of spiral galaxies, and she needed eyes, millions of them. By 2009, she had published 22 papers with over 5,600 citations, and then she left academia. She was not keen on the postdoc circuit, she said, moving every few years with no stability, no ability to plan a life. She went into quantitative finance in London. There is something quietly devastating about that. One of the two people who named the most disturbing anomaly in modern cosmology decided the field was not a place where she could build a future. She left. The anomaly did not. And then there is George Efstathiou, who represents the other side of this story. Efstathiou is the anomaly's most prominent skeptic and one of the most decorated cosmologists alive. His origin story is improbable by the standards of elite British science. The son of Greek Cypriot immigrants who ran a fish and chip shop in North London, he left school at 16 and went on to become one of the most cited scientists on Earth. Over 400 papers, more than 130,000 citations, Fellow of the Royal Society, Gold Medal of the Royal Astronomical Society, Director of the Kavli Institute for Cosmology at Cambridge. As chair of the Cambridge Planck Analysis Centre, he had direct, hands-on access to the best CMB data in existence. Efstathiou has consistently maintained that the anomalies reflect what statisticians call a posteriori reasoning. The argument goes like this. If you look at a complex dataset and search for patterns without specifying in advance what patterns you are looking for, you will find some. The more tests you run, the more anomalies you will discover, simply because some fraction of any random dataset will appear non-random by whatever metric you happen to apply. The look elsewhere effect, the statistical penalty for multiple testing, should deflate the significance of the CMB anomalies to uninteresting levels. His 2010 paper directly contested the Copy-Hutra-Schwarz-Starkman analysis, arguing that their Bayesian framework could not exclude the lambda CDM model at any meaningful level. It is a serious argument. It is also, in this specific case, weaker than it sounds. The look elsewhere effect applies most strongly when you go hunting for patterns with no prior motivation. But the CMB anomalies were discoveries, not searches. The alignment was found in the data, not hypothesized and then tested. And crucially, the anomalies survived the transition from WMAP to Planck, which is the equivalent of an independent replication. You cannot explain away a result by invoking the look elsewhere effect if the result has been independently confirmed by a different experiment. That is what confirmation means. Even Efstathiou seems to sense the tension. In a moment of candor that reveals more than his published papers, he said, "Our ultimate goal would be to construct a new model that predicts the anomalies and links them together. But these are early days. So far, we do not know whether this is possible and what type of new physics might be needed. And that is exciting. Even the chief skeptic finds it exciting. Even the person most committed to defending the standard model acknowledges that new physics might be needed. That admission, wrapped in qualification and hedged with caution, is more revealing than anything in his formal publications." So the data is real, confirmed by 2 missions, 8 releases, 4 algorithms, 3 independent research groups. Over 20 years, the community's best skeptic acknowledges new physics may be required, and the anomalies refuse to go away, which means somebody needs to explain them. And this is where the story becomes a graveyard. The most conservative explanation is the one the establishment preferred for years: foreground contamination. The Milky Way is a messy environment. Thermal radiation from galactic dust, synchrotron radiation from electrons spiraling through the galaxy's magnetic field, free emission from ionized hydrogen gas. All of this radiates at microwave frequencies and contaminates the CMB signal, especially near the galactic plane where the emission is brightest. If you strip it away imperfectly, if your foreground model misses some component, or subtracts too much in one direction and too little in another, you could introduce artificial alignments into the cleaned CMB map. For years, this was the safe bet, a boring, methodological explanation that would let everyone go back to business as usual. It does not work. And the reason it does not work is simple enough to state in one sentence. Galactic foregrounds produce galactic alignments, not ecliptic ones. The galaxy and the ecliptic are tilted about 60 degrees relative to each other. If residual galactic emission were responsible for the observed anomalies, the preferred direction would point along the galactic plane. It does not. It points along the ecliptic. The foreground explanation does not just fail to explain the data, it fails to explain the single most distinctive feature of the data. But in 2023, something genuinely interesting happened. Hansen, Banday, Gorski, Hevon and Reinecke published a paper documenting a previously unknown contamination source. They found systematic temperature decrements around nearby large spiral galaxies in the Planck data, correlating with the CMB at multipoles L equals 2 through 5. This is a real detection of a real foreground that nobody had accounted for. It is tantalizing because it provides for the first time a physical mechanism that could contribute to the large-scale anomalies. But the physical mechanism itself is unidentified. Nobody knows why nearby galaxies would produce correlated temperature shifts in CMB maps, and the effect has not been demonstrated to fully account for the observed alignments or the ecliptic correlation. It is a clue, a genuine, interesting, important clue. But it is not a solution, and a clue without a mechanism is a promise, not an explanation. So maybe the answer is more radical. Maybe the universe itself is geometrically anisotropic, not just its foregrounds, but the fabric of space-time. The Italian mathematician Luigi Bianchi classified homogeneous but anisotropic solutions to Einstein's field equations back in the 19th century. In 2005, Jaffe, Banday, Ericsson, Gorski, and Hansen showed that a specific Bianchi type 7 sub H cosmology could simultaneously reproduce the low quadrupole, the multipole alignments, and the power asymmetry. It was elegant. It was exciting. For a brief window, it looked like the answer. It required a total density parameter, omega total, of 0.5. The measured value from multiple independent methods is 1.0, give or take a few tenths of a percent. A universe with omega total of 0.5 would be wildly open, negatively curved, expanding far faster than observed, and completely inconsistent with essentially every other cosmological dataset. 2 years later, Ponson and Chalinor calculated the polarization predictions of Bianchi models and showed they would overproduce B-mode polarization far beyond observational upper limits. The Planck collaboration later confirmed that while fitting a phenomenological Bianchi template to the data provides a mild statistical improvement, physically self-consistent Bianchi models that actually obey general relativity with realistic matter content are strongly disfavored. The geometric anisotropy explanation is dead. What about a primordial magnetic field? If a large-scale, coherent magnetic field existed in the universe before the CMB was released, it would break isotropy in the primordial plasma, creating a preferred direction in the temperature fluctuations. Campanelli, Sia, and Tedesco published a paper in Physical Review Letters in 2006 showing that a uniform magnetic field of about 4 to 5 nanoausis could make the early universe slightly ellipsoidal with an eccentricity of roughly 3.5 times 10 to the minus 3. This would suppress the quadrupole along the field direction, explaining its anomalously low power. The required field strength is not obviously ruled out by other observations. It is a real possibility, but it does not explain the ecliptic correlation. A primordial magnetic field imprints a cosmic preferred direction, one determined by the initial conditions of the universe. There is no reason that direction should align with the orbital plane of a star system that would form 9 billion years later, unless you invoke an extraordinary coincidence, which is the very thing the magnetic field hypothesis was supposed to avoid. Perhaps the problem is not the geometry of the universe, but its topology. This is an important distinction that often gets lost. General relativity describes the local curvature of space-time, how space bends in the presence of mass and energy. But general relativity says nothing about the global topology, the overall shape and connectedness of space. A flat universe could be infinite, stretching forever in all directions, or it could be finite and wrapped around on itself, like the surface of a torus or the faces of a dodecahedron, where traveling far enough in one direction brings you back to where you started. Both options are consistent with the same local geometry. General relativity cannot distinguish between them. In a finite universe with non-trivial topology, the longest wavelength modes of the CMB are suppressed, not because of any exotic physics, but because of simple geometry. The modes physically cannot fit. You cannot have a wavelength longer than the space it exists in. The same way you cannot fit an ocean wave into a bathtub. The CMB's low quadrupole, the missing large angle correlations, the strange behavior of the largest modes, all of these are exactly what you would predict if the universe is not much bigger than the observable horizon. If the total size of reality is comparable to the distance light has traveled since the Big Bang, roughly 46 billion light-years, to the edge of the observable universe, then the modes sensitive to scales larger than that size would be cut off. They would be suppressed. They would behave anomalously. Jean-Pierre Luminet and colleagues proposed a specific model in Nature in 2003. The Poincaré dodecahedral space, a positively curved, finite universe with the topology of a regular dodecahedron, 12 pentagonal faces with opposite faces identified. It naturally suppresses the quadrupole. It explains the missing large-angle correlations. It is elegant and testable. If the universe had this topology, you would see matching temperature patterns, called matched circles, in opposite parts of the CMB sky, where the identified faces overlap. Multiple groups searched for matched circles in WMAP and Planck data. The results range from ambiguous to negative. No definitive detection has been made, and even if the topology were correct, it would not explain the ecliptic alignment. The shape of the universe has no reason to care about the orbital plane of one star. The multiverse made a brief appearance through the mechanism of bubble collisions. In eternal inflation, our observable universe is a bubble that nucleated within a larger inflating space-time. Other bubbles may have formed nearby and collided with ours, leaving a signature in the CMB, a disk-shaped temperature anomaly. Feeney, Johnson, Mortlock, and Peiris searched for these signatures in WMAP data in 2011. They found no evidence. And once again, there is no reason a collision from a random neighboring bubble universe would produce a preferred direction aligned with the ecliptic. Anisotropic inflation was the next hope. Ackerman, Carroll, and Wise proposed in 2007 that a vector field active during inflation could break isotropy at a fundamental level, producing a direction-dependent power spectrum. This got briefly exciting in 2009, when Groenboom and Ericsson claimed a 9 sigma detection of such anisotropy in the WMAP 5-year data. 9 sigma. That would have been the discovery of the century. It turned out to be an artifact of WMAP's asymmetric beam response. When the data was corrected for beam effects, the signal vanished. The 9 sigma detection was instrumental, not cosmological. Anisotropic inflation remains theoretically possible. It has no confirmed observational support. Loop quantum cosmology takes a different approach entirely. Developed primarily by Abhay Ashtekar and collaborators, it replaces the Big Bang singularity with a quantum bounce. Instead of the universe beginning from a point of infinite density, it was previously contracting, reached a maximum density set by quantum gravity effects at roughly 94% of the Planck density, and then rebounded into the expansion we observe. This bounce can excite the very largest modes of the CMB, the low L multipoles, in a way that naturally explains the suppressed quadrupole and the odd parity dominance. A 2021 paper showed that the bounce generates non-Gaussian correlations consistent with several of the observed anomalies. It is the most theoretically grounded explanation on the table. It emerges from a serious quantum gravity framework, not from ad hoc parameter tuning. But it does not explain the directional alignment. Loop quantum cosmology produces anomalous amplitudes, not anomalous orientations. It can tell you why the quadrupole is too weak. It cannot tell you why it points toward the ecliptic. It treats the symptoms while leaving the disease undiagnosed. The most recent proposal is direct sum inflation, published by Gastanaga and Kumar in 2024. It claims to be 50 to 650 times more probable than standard slow-roll inflation for generating the observed parity asymmetry. The paper is provocative, and the framework is novel. It is also in very early development and, like every other proposal on this list, does not address the ecliptic correlation. You see the pattern now. Every proposed explanation for the axis of evil either fails on the ecliptic alignment specifically, requires parameters wildly inconsistent with other observations, or has been killed by polarization constraints. The ecliptic alignment is the feature that no theory can account for. It is the residue that survives every attempted cleaning. An unexplained preferred direction in the CMB would be strange, but theoretically addressable. An unexplained preferred direction that happens to coincide with the orbital plane of our solar system, a structure 9 billion years younger than the signal itself, is something else entirely. It is either the most extraordinary coincidence in the history of empirical science, or evidence of something so far outside current theoretical frameworks that nobody knows where to begin. And here is what makes that worse. It is not that nobody has tried. The explanations above represent 2 decades of work by competent physicists. Bianchi models, primordial fields, non-trivial topology, bubble collisions, modified inflation, quantum bounces. Each one was motivated by real physics and developed by serious people. The graveyard is not full of crackpot theories. It is full of legitimate, peer-reviewed, mathematically rigorous proposals that all share one thing in common. They all break against the same rock, the ecliptic alignment, the one feature that turns a strange cosmological anomaly into something that feels personal. Because it is not just a preferred direction in the universe, it is a preferred direction that appears to point at you. The rational response to this situation, 2 decades of confirmed data with no surviving explanation, would be a massive mobilization of theoretical and observational resources, a dedicated research program, targeted observations, conference sessions, PhD theses, funding, the kind of response the physics community routinely produces when confronted with persistent anomalies at this level of statistical significance. That is not what happened. What happened instead is one of the strangest sociological episodes in modern physics, a confirmed anomaly that challenges the foundational assumption of the field, verified by 2 independent space missions, investigated in depth by a core group of 4 people, and largely ignored by everyone else. Not denied, not debunked, ignored, sidelined, treated with the kind of polite disinterest you might show a relative who brings up conspiracy theories at Thanksgiving dinner. Except in this case, the relative has a Guggenheim Fellowship, and the conspiracy is published in physical review letters. To understand why the physics community responded this way, you have to understand something about how science actually works when it encounters evidence it cannot process. Because the official story, the one scientists tell themselves, is that science follows the evidence wherever it leads, that anomalies are exciting, that paradigm shifts are the highest calling of the discipline. And all of that is true in retrospect. It is true in the textbooks that describe revolutions after they have already happened. It is not true in the moment when the anomaly is live, when the evidence threatens the work you have built your career on, when engaging with it carries real professional risk and no obvious professional reward. The axis of evil exists in exactly that space. And what happened to it tells you more about how modern physics operates than any Nobel lecture ever will. Consider the numbers. The muon G-2 anomaly, the discrepancy between the measured and predicted magnetic moment of the muon, reached a peak significance of about 4.2 sigma. It is a particle physics anomaly with a clear experimental path. Build a more precise experiment. Measure again. It has a rich, theoretical landscape. New particles, supersymmetry, leptoquarks, dark photons, any of a dozen frameworks can accommodate a muon anomaly. Working on it is safe. The career risk is near zero. The potential payoff is enormous, and it has mobilized hundreds of physicists, thousands of theoretical papers, hundreds of millions of dollars in experimental infrastructure, front page coverage in every major newspaper. The axis of evil rejects isotropy at greater than 99.9% confidence. It has been confirmed by 2 independent space missions over 20 years. The combined probability of the observed anomaly pattern arising by chance is less than 0.008%, and the number of physicists who have made it the focus of their research career can be counted on one hand. The number of dedicated experiments designed to test it is 0. Now that CMB S4 has been cancelled, the number of PhD theses specifically addressing it in a field that produces thousands of theses per year is vanishingly small. The disparity between the response to G-2 and the response to the axis of evil is not about significance. It is about tractability. It is about career incentives. And it is about something darker, which is the psychological difficulty of confronting evidence that, if taken seriously, would require you to question the foundation of everything your field has built over the past 3 decades. And then there is the contamination, not galactic contamination, ideological contamination, the kind that makes serious scientists reflexively distance themselves from serious data. In 2014, a documentary called The Principle was released. It was produced by Robert Sungenis, a Catholic traditionalist who believes, literally, that the Earth is the stationary center of the universe and that the Sun orbits around it. Geocentrism, the pre-Copernican model. Sungenis used the CMB anomalies and specifically the ecliptic alignment that defines the axis of evil as the central evidence for his argument. The film's thesis, stated without irony, was that modern physics had accidentally confirmed what the medieval church taught all along, that the Earth is special, that you are at the center, that Copernicus was wrong. The film included interview clips with Lawrence Krauss, Michio Kaku, Max Tegmark, and Julian Barbour. All of them later said the clips were taken out of context, recorded for other purposes, or under misleading pretenses, and edited to support a thesis they found absurd. Krauss wrote a furious essay in Slate describing the film as an example of the nonsensical notion that Earth is the center of the universe, and demanding that his participation not be interpreted as endorsement. Tegmark publicly disavowed any connection to the project. The geocentrists, of course, did not care. They had their film, they had their clips, and they had, whether the physics community liked it or not, real data. The ecliptic alignment is real. It has been confirmed. It does point toward the plane of Earth's orbit. Those are facts. The geocentrists' interpretation of those facts is laughable, but the facts themselves are not. And that is what made the principle so damaging, not to geocentrism, which remains exactly as ridiculous as it was before the film, but to the anomaly itself, to the scientists studying it, to the career prospects of anyone who might want to investigate it. After the principle, working on the axis of evil carried an additional risk beyond the normal career penalties of studying intractable anomalies. It carried the risk of association, of being lumped in with flat earthers and young earth creationists and geocentrists, of having your research cited approvingly in documentaries funded by religious extremists. The four physicists who continued to study the anomaly, Kopy, Huterer, Schwartz, and Starkman, had the tenure, the citations, and the institutional standing to absorb that risk. A postdoc did not. A graduate student did not. An untenured assistant professor at a research university, dependent on grant funding and peer review for career survival, absolutely did not. And so the pool of people willing to study the most disturbing anomaly in observational cosmology shrank to the handful who could afford the professional cost of being associated with it. There is a study that documents this effect with uncomfortable precision. A 2017 paper in Studies in History and Philosophy of Science examined how graduate-level cosmology textbooks handle observational anomalies that are incompatible with the lambda CDM model. The CMB anomalies were the primary case study. The findings were blunt. The textbooks systematically omit them. They teach the acoustic peaks, the precision power spectrum, the concordance between CMB baryon acoustic oscillations and type Ia supernovae. They present lambda CDM as confirmed, validated, a triumph of modern physics. The large-scale CMB anomalies, the ones that have been confirmed at 3 sigma by 2 independent space missions, the ones that challenge the foundational assumption of the model the textbooks are teaching, simply do not appear. They are not discussed as open questions. They are not flagged as unresolved tensions. They are not mentioned at all. Think about what that means for the next generation of cosmologists. They finish their graduate training having never encountered the anomaly. They enter the field believing the cosmological principle is observationally confirmed at all scales. They write proposals, design experiments, and build careers on a foundation they have never been shown is cracked. The omission is self-reinforcing. If the textbooks do not mention it, it must not be important. If it is not important, it does not belong in the textbooks. The loop closes. The anomaly persists in the data and disappears from the curriculum, and an entire generation of physicists learns to look at the CMB without seeing what is actually in it. And what is actually in it, at these larger scales, is not just one anomaly. That is the thing that gets lost in the debate over statistical significance. Critics like Evstathiou focus on each anomaly individually and argue, correctly, that a single 2 to 3 sigma deviation is not compelling evidence for new physics. They invoke the look elsewhere effect and point out that in a rich dataset, you expect to find some unusual features. All of that is true in isolation, but the anomalies are not isolated. Consider the cold spot. It sits in the southern galactic sky toward the constellation Eridanus at galactic coordinates of roughly 208 degrees longitude, minus 56 degrees latitude. It is a region about 5 degrees across, where the CMB temperature is depressed by 70 to 140 microkelvin below the surrounding sky. On its own, a cold patch in the CMB is not unusual. The fluctuations are random, and random distributions produce outliers. What makes the cold spot anomalous is its profile. It is not just cold. It is surrounded by an unusually hot ring, creating a temperature gradient that is steeper than virtually anything in lambda CDM simulations. The combined cold center plus hot ring profile has a probability of roughly 1 in 200 of occurring by chance, depending on the analysis. There was a brief moment of hope that the cold spot could be explained by the integrated Sachs-Wolf effect. When CMB photons pass through a large void in the cosmic web, they lose a tiny amount of energy because the void is expanding and the gravitational potential is changing while the photons traverse it. In 2015, Istvan Sapudi and colleagues identified a supervoid in the direction of the cold spot, roughly 1.8 billion light-years across, centered at a redshift of about 0.22. It was real, it was big, and it was in the right direction. For a moment, it looked like the cold spot might have a boring, local explanation, but the math did not work. The integrated Sachs-Wolf effect from a void of that size and depth produces a temperature decrement of about 10 to 20 microkelvin. The cold spot is 70 to 140. The void explains, at most, 10 to 20% of the observed signal. The rest remains unexplained. Now here is the thing that should bother you. The cold spot is not aligned with the axis of evil. It sits at a different location in the sky, in a different direction. You might think that weakens the case that the anomalies are connected. It does the opposite. The cold spot anomaly occurs at the same angular scales as the other anomalies, the largest scales in the CMB. It involves the same low L multipoles, and it defies the same model, lambda CDM, at the same level of significance. The question is not whether each anomaly is individually compelling. The question is why the largest scale modes of the CMB are anomalous in so many independent ways simultaneously. The quadrupole is too low. The octupole is too planar. They share an axis. That axis correlates with the ecliptic. The large angle correlations are missing. The parity is skewed. The power is asymmetric between hemispheres. And there is an unexplained cold spot with a profile that simulations almost never produce. Every one of these is a 2 to 3 sigma anomaly in isolation. Together, they constitute a pattern of misbehavior at the largest scales that cannot be dismissed by pointing at any single member of the family. It is the difference between finding one unusual card in a shuffled deck and finding that the entire bottom half of the deck is sorted by suit. One unusual card means nothing. A systematic pattern means the deck was not shuffled the way you thought. This is not conspiracy. That word gets thrown around too easily, and it implies coordination, secrecy, intent. What is happening with the axis of evil is more mundane and in some ways more troubling. It is the natural behavior of a mature scientific field confronted with evidence it has no framework to process. The cosmological principle is not just one assumption among many. It is the load-bearing wall. Pull it out and you do not get a remodeled house. You get rubble. The FLRW metric fails. Distance measurements become direction dependent. The evidence for dark energy changes. The concordance model, the thing that won Nobel Prizes and fills textbooks and organizes the entire research enterprise, stops being concordant. Nobody is going to volunteer for that demolition project, especially not when the alternative, ignoring the anomaly and hoping it resolves itself, has no immediate professional cost. And then, on July 9th, 2025, the slow-motion institutional failure became acute. The United States Department of Energy and the National Science Foundation jointly announced that they could no longer support the CMB S4 project. CMB S4 was the planned next-generation ground-based CMB experiment. 500,000 detectors spread across 2 sites, one in the high Atacama Desert in Chile and one at the South Pole in Antarctica. It had been ranked the #1 priority by the 2023 Particle Physics Project Prioritization Panel, the P5 report that sets the direction of American particle physics and cosmology for a decade. It was supposed to measure CMB polarization with sensitivity and order of magnitude beyond anything currently possible. And polarization is the test. If the axis of evil is primordial, if it reflects a real feature of the early universe, then it should appear not just in the temperature of the CMB, but in its polarization pattern. Specifically, the E-mode polarization should be correlated with the temperature anomalies. Temperature and E-mode are generated by the same physics at the surface of last scattering. If the temperature is anomalous and the anomaly is real, the polarization must show it. If the anomaly is caused by foregrounds or local effects that contaminate only the temperature measurement, the polarization should be clean. CMB S4 would have answered the question. Budget constraints and the ballooning cost of Antarctic infrastructure killed it. The project had grown from its initial estimates. The logistics of operating at the South Pole had become more expensive than projected, and the budgets of both DOE and NSF were under pressure from competing priorities. The science collaboration issued a statement saying it was exploring alternative paths forward, but the timeline has been pushed out indefinitely. The #1 priority experiment in American cosmology, the one that could have resolved a 20-year-old anomaly, challenging the foundational assumption of the field, was cancelled because it cost too much. That leaves one mission: LIGHTBIRD, the light satellite for the study of B-mode polarization and inflation from cosmic background radiation detection. It is a Japanese Aerospace Exploration Agency mission, a full-sky CMB polarization satellite carrying 15 frequency bands and approximately 4,000 superconducting transition edge sensor detectors. Unlike ground-based experiments, which can only observe a portion of the sky and are limited by atmospheric emission at large angular scales, LIGHTBIRD will map the entire sky from orbit with full sensitivity to the lowest multipoles where the axis of evil lives. It is designed primarily to detect the curl-like B-mode polarization signature of primordial gravitational waves from inflation, but its full sky E-mode maps will also provide a definitive test of whether the CMB temperature anomalies are mirrored in polarization. LIGHTBIRD has had a complicated path. In 2024, KKK, the Japanese high-energy physics laboratory that was providing critical superconducting detector technology, relinquished its contribution to the mission, forcing a redesign. JAXA approved the mission to proceed in September 2025, with revised specifications and a new target launch date in Japanese fiscal year 2032. That is 7 years from now. At minimum, space missions rarely launch on time. Delays of 2 to 3 years are common. The Planck satellite itself was approved in 1996 and did not launch until 2009. If LIGHTBIRD follows a similar trajectory, the definitive polarization test of the axis of evil may not arrive until the mid-2030s. You might ask about the Simons Observatory, which achieved first light in February 2025 from its site in the Atacama Desert. It is a serious experiment with impressive sensitivity, and it will produce valuable CMB polarization data over the coming years. But ground-based observatories have a fundamental limitation when it comes to the axis of evil. They can only see part of the sky. The atmosphere, the terrain, the location on Earth's surface all constrain the observable area, and the anomalies live at the very largest angular scales, L equals 2 and 3, modes that span 60 to 90 degrees across the sky. To measure these modes properly, you need the full sky. Every piece of missing sky introduces uncertainty, requires modeling, and degrades your ability to characterize the lowest multipoles. A full sky satellite is not a luxury for this measurement. It is a necessity. The Simons Observatory will contribute important data at intermediate scales, but it cannot replace what Lightbird will provide for the specific question of whether the axis of evil appears in polarization. So the timeline is what it is. 7 years to Lightbird at the earliest, possibly a decade or more. And in the meantime, the anomaly sits in the temperature data, confirmed and unexplained, waiting for a polarization measurement that keeps getting pushed further into the future. 30 years after the anomaly was first detected in WMAP data. 30 years of a confirmed, unexplained feature sitting in the most fundamental dataset in cosmology. 30 years before anyone builds an instrument capable of answering the most obvious next question about it. You should be angry about that. Not because the cancellation of CMB S4 was some kind of conspiracy. It was a budget decision, but because the budget decision reveals what the field actually values versus what it claims to value. Cosmologists say anomalies are exciting. They say paradigm shifts are the highest calling of physics. They say they follow the evidence wherever it leads. And then, when the evidence leads somewhere uncomfortable, when the anomaly is intractable and the theoretical landscape is barren and the career incentives point away from engagement, they let the one experiment that could resolve it die of bureaucratic neglect, while the data sits there, year after year, confirmed and unexplained and ignored. And that brings us to the last descent, the place where the story stops being about politics and funding and sociology and becomes about something harder to sit with. Because if you strip away all the noise, all the institutional dysfunction, all the human failure, what remains is a question that the data has been asking for 20 years and that nobody has answered. And the reason nobody has answered it may not be that they have not tried hard enough. It may be that the answer is not accessible to us. Forget the ecliptic alignment for a moment. Set it aside. It is the feature that makes the axis of evil feel personal, the thing that gives it its name and its unease. But it may also be a distraction from what the anomaly is actually telling us. Focus instead on what the data looks like if you ignore the local correlation and just ask what the universe is doing at its largest scales. The affected modes, L equals 2 through 5, are not just any modes. They are the ones that span the entire observable universe. Their wavelengths correspond to physical scales of billions of light years, comparable to the distance from here to the edge of the observable cosmos. They are the modes most sensitive to the global properties of reality, not the contents of the universe, the galaxies and clusters and voids, the container, the geometry, the topology, the boundary conditions, if there are any. At smaller scales, L equals 30 and above, the CMB is a triumph. The power spectrum matches lambda CDM with astonishing precision. Every acoustic peak, every trough, every damping feature falls exactly where the model predicts. This is because the small-scale CMB is determined by well-understood local physics, sound waves in the primordial plasma, photon diffusion, the recombination process. These are phenomena that depend on the constituents of the universe, the ratio of matter to radiation, the baryon fraction, the Hubble constant, but not on the global geometry of space. You can change the topology of the universe without affecting the acoustic peaks. The small-scale CMB is insensitive to the shape of reality. It sees the furniture. It does not see the room. The large-scale CMB sees the room, and the room looks wrong. If you want to understand why that matters, why it is not just an academic curiosity for specialists, consider what happens to the rest of cosmology if the room really is shaped differently than everyone assumed. The FLRW metric, the mathematical foundation of the concordance model, is derived under the assumption that space is homogeneous and isotropic. Remove that assumption, and the metric changes. In an anisotropic universe, distances depend on direction. A supernova at a given redshift in one direction of the sky could be at a different physical distance than a supernova at the same redshift in a different direction. The relationship between redshift and distance, the cornerstone of observational cosmology, becomes direction dependent. The 1998 supernova measurements that revealed the accelerating expansion of the universe, the discovery that dark energy exists, were calibrated against an isotropic background. If the background is not isotropic, those calibrations shift. The amount of dark energy changes. Possibly, its nature changes. In some anisotropic models, part of what we attribute to dark energy, the mysterious component that makes up roughly 68% of the energy content of the universe, could be reinterpreted as an artifact of assuming isotropy when isotropy does not hold. That is not idle speculation. Subir Sarkar, a theoretical physicist at Oxford, who has been one of the most persistent critics of the standard cosmological model, has argued for years that the evidence for accelerating expansion is weaker than commonly claimed once you relax the isotropy assumption. His analyses of the supernova data, treating the expansion rate as potentially direction-dependent, produce fits that do not require dark energy at all. The mainstream response has been dismissive. Sarkar's position remains a minority view. But the point is that it exists, that the mathematics permits it, and that the only thing preventing it from being taken more seriously is the assumption of isotropy, which is exactly the thing the CMB anomalies call into question. If the universe is anisotropic, the consequences do not stop at dark energy. The cosmic distance ladder, the chain of measurements linking nearby objects to distant ones that underpins essentially all of extragalactic astronomy, assumes an isotropic expansion. The baryon acoustic oscillation measurements, the patterns in the distribution of galaxies that provide an independent check on the expansion history, assume isotropy in their analysis. The CMB power spectrum itself, the precision measurement of acoustic peaks that is the crown jewel of lambda CDM, is analyzed under the assumption that the statistical properties of the fluctuations do not depend on direction. If they do, the extracted cosmological parameters, the age of the universe, the Hubble constant, the matter density, all of them acquire an additional uncertainty that no current error bar accounts for. This is what it means for the cosmological principle to be load-bearing. The cosmological principle does not sit alongside other assumptions as one among equals. It is the assumption that makes all the other measurements interpretable. Remove it, and you do not get a slightly different cosmology. You get a fundamentally different epistemological situation, in which the measurements still exist, but their meaning becomes uncertain. If the universe is infinite and flat, as the lambda CDM model assumes, the lowest multipoles should display the full range of random Gaussian variation. There is no constraint on them. The statistical properties of the quadrupole and octupole should be determined entirely by the physics of inflation, which generates random fluctuations with no preferred direction, no preferred amplitude, no preferred parity. What you observe should look like a random draw from that distribution. What you observe does not look like a random draw. The quadrupole is too weak. The octupole is too planar. They share an axis. The large angle correlations are missing. The parity is wrong. All of these features point in the same direction. Something is constraining the largest modes. Something is limiting them. Something is confining their behavior in a way that the infinite, flat, featureless spacetime of lambda CDM does not predict. In a finite universe, this makes sense. Not exotic sense, not speculative sense, geometric sense. If the universe has a topology, if space wraps around on itself in some configuration, then modes with wavelengths larger than the characteristic size of the universe cannot exist. They are cut off. The modes that approach that characteristic size are suppressed and distorted, their statistical properties altered by the global geometry in ways that an infinite universe would never produce. The low quadrupole, the missing large angle correlations, the anomalous alignment of the largest modes, all of these would be natural consequences of a universe that is finite and not much larger than the observable horizon. Glenn Starkman knows this. It is why he now leads the Compact Collaboration, a multi-institutional effort dedicated to searching for the signatures of cosmic topology in CMB data. The collaboration's approach is systematic. They are not looking for any one topology. They are developing the mathematical framework to test a wide range of possible topologies against the Planck data, searching for the subtle correlations between widely separated points on the sky that would betray the repeating structure of a finite space. The work is slow, computationally expensive, and unglamorous. It does not produce headlines. It produces constraints, limits on what the topology could be. And constraints in science are how you close in on the truth. To appreciate what is at stake, think about what it would mean for the universe to have a topology, not in the abstract mathematical sense, but in the physical, tangible sense. If the universe is a 3 torus, the simplest closed flat topology, then space wraps around on itself in all 3 spatial dimensions. If you could travel far enough in any direction without stopping, you would eventually return to where you started. Not because the universe curves back on itself like the surface of a sphere, but because the boundaries are identified like the edges of a video game screen, where going off the right side puts you on the left. In such a universe, every point is surrounded by an infinite lattice of copies of itself. You are not in one location. You are in every location, repeated across the torus, an infinite number of you stacked in every direction. And the CMB, the oldest light, would carry the fingerprints of this repetition. Light from the same physical region of the early universe would reach you from multiple directions, having traveled different paths around the torus, creating correlated patterns in widely separated parts of the sky. Nobody has found those correlations definitively. The matched circle searches in Planck data placed lower limits on the size of a toroidal universe, roughly equal to the diameter of the last scattering surface, about 93 billion light-years. Smaller tori are ruled out. Larger tori, those with a characteristic scale somewhat bigger than the observable universe, could still be hiding in the data. They would not produce matched circles because the repeated images would be too far apart to overlap within our observable horizon. But they would still affect the lowest multipoles. They would still suppress the quadrupole. They would still distort the statistical properties of the largest modes. The universe could have a shape that we can detect only through its effects on the lowest frequency vibrations of the CMB. A shape that is too large to see directly, that extends beyond the observable horizon, that we can only infer from the faintest distortions it imprints on the oldest light. Like hearing the resonant frequency of a room and deducing the dimensions of the room from the sound alone, without ever being able to see the walls. But here is the thing about topology that makes the whole picture more unsettling, not less. If the universe is finite, if space has a shape, that shape was determined before inflation. The topology of space is a feature of the initial conditions. Inflation can stretch the universe. It can smooth the universe. It can drive the observable portion of the universe very close to flat, but it cannot change the topology. A torus before inflation is still a torus after inflation, just a much larger torus. The same is true for a dodecahedral space, or a 3 torus, or any other finite topology. The shape is preserved through the exponential expansion. It is a primordial feature, a relic of whatever existed before inflation, or a relic of whatever process gave rise to inflation itself. And the CMB anomalies, the ones that are sensitive to the global geometry, are the only data we have that could reveal that shape. They are the only observations capable of seeing past inflation's smoothing, because they operate at scales large enough to feel the topology. Everything else in cosmology, every galaxy survey, every supernova measurement, every baryon acoustic oscillation detection, operates at scales small enough that the topology is invisible. The large-scale CMB is our one window, and the view through that window is anomalous. There is another piece of evidence that arrived recently, and that makes the isotropy question even harder to ignore. It has nothing to do with the CMB directly, and it comes from a completely different community using completely different methods. The cosmic radio dipole. The logic is straightforward. Our motion through the CMB rest frame creates a dipole in the microwave background. One side of the sky slightly hotter, the other slightly cooler, with an amplitude of about 3.35 millikelvin, corresponding to a velocity of 369 kilometers per second. This motion is well measured and uncontroversial. If our motion is the sole cause of the dipole, then when we look at distant objects, radio galaxies and quasars at cosmological distances, we should see a matching effect. There should be slightly more sources in the direction we are heading, because our motion compresses the observed distribution, and slightly fewer behind us. The amplitude and direction of this matter dipole should match the CMB dipole exactly. The direction matches. The amplitude does not. Nathan Secrest and colleagues in a series of papers culminating in a 2025 review published in Reviews of Modern Physics, have measured the matter dipole using catalogues of millions of radio sources and infrared selected quasars. Across multiple independent surveys, the matter dipole is roughly twice as large as the CMB kinematic prediction. The combined significance is approximately 6.4 sigma. 6.4 sigma is above the 5 sigma discovery threshold that particle physics uses to claim new phenomena. If a particle physics experiment reported a 6.4 sigma discrepancy with the standard model, it would be front-page news. It would trigger emergency theory workshops. It would redirect entire research programs. The cosmic dipole anomaly independently challenges the cosmological principle, because if our motion is the sole cause of the CMB dipole, the matter dipole must match. It does not. The discrepancy means one of 3 things. Our motion through the universe is more complicated than a simple velocity, involving acceleration or a local bulk flow that affects nearby matter but not the CMB. Or the matter distribution is genuinely anisotropic at large scales, with more structure in one direction than the other, which directly violates isotropy. Or the CMB dipole itself is not entirely kinematic. Part of it may be primordial, a real temperature asymmetry imprinted at the time of last scattering that we have been mistakenly subtracting from the data for decades, misinterpreting it as our local motion. If even a fraction of the CMB dipole is primordial, the implications cascade. Every CMB analysis that subtracts the dipole as a kinematic artifact would need to be redone. The inferred properties of the primordial fluctuations would change. The cosmological parameters would shift. Add it up. The axis of evil at greater than 3 sigma, confirmed by 2 missions, the missing large angle correlations at 3.5 sigma, the parity asymmetry at greater than 2.5 sigma, the hemispherical power asymmetry at 3 sigma, the cold spot with its unexplained profile, and now the cosmic dipole anomaly at 6.4 sigma from a completely independent dataset using completely different methods, all pointing in the same direction. The universe appears to be lopsided. It has structure at its largest scales that the standard model does not predict and cannot accommodate. And the reaction from the field, even now, even with the dipole anomaly well above the discovery threshold, is muted compared to what you would expect. The Seacrest et al. Result was published in Reviews of Modern Physics, one of the most prestigious review journals in all of physics. It has generated discussion. It has generated follow-up analyses, but it has not generated the kind of mobilization you saw with the Higgs boson discovery, or the gravitational wave detection, or the muon anomaly. There are no emergency workshops. There are no redirected research programs. There are no front-page headlines declaring that the foundational assumption of cosmology is in trouble. Part of the reason is technical. The cosmic dipole measurement depends on the careful calibration of large radio surveys, and there are legitimate debates about whether selection effects and survey systematics are fully under control. The Catwise quasar sample that Seacrest and colleagues used covers over 1.3 million sources, making it one of the largest cosmological catalogues ever assembled. But every large survey has its peculiarities, and teasing out a genuine cosmological signal from instrumental and astrophysical systematics is never trivial. These are real concerns, and they deserve serious engagement. But the engagement has been disproportionately focused on finding reasons the result might be wrong, and disproportionately quiet about what it means if it is right. This is a pattern you see throughout the history of anomalies that threaten foundational assumptions. The community invests enormous energy in explaining the result away, and comparatively little in exploring the implications of the result being real. It is human nature. It is institutional nature. And in this case, the implications of the result being real are so destabilizing to the existing framework that the asymmetry of effort is, if not justified, at least understandable. Because if the cosmic dipole anomaly is real, and if the CMB anomalies are real, and if the cosmological principle does not hold at the largest scales, then the project of precision cosmology, as currently practiced, rests on a faulty assumption, not in a way that invalidates the small-scale results, the acoustic peaks, the baryon fraction, the basic thermal history of the universe. Those are robust. They depend on local physics that is well understood, but in a way that introduces uncontrolled, systematic uncertainty into every measurement that probes the largest scales, or that relies on the assumption of isotropy to interpret distances and volumes. And that is most of cosmology beyond the CMB itself. And the deepest question is not what the anomaly is, it is what it means. If the universe has a preferred direction, a measurable, confirmed, persistent preferred direction that survived inflation and has persisted for 14 billion years, then that direction was encoded at the birth of the universe, before inflation stretched the cosmos to its current scale, before the hot Big Bang filled space with particles and radiation, before the CMB was emitted, before matter condensed into galaxies, before stars ignited, before heavy elements were forged, before the earth formed, before life arose, before you existed, something, some process, some principle, some condition determined that reality would have an orientation, that space would have a shape, that the laws of physics would operate in a universe with a built-in direction. And whatever determined that is, by definition, prior to the universe as we understand it, it belongs to the initial conditions. It belongs to whatever mechanism selected our particular cosmos from the space of possible cosmoses. It belongs to the question that inflation was specifically designed to render unanswerable, the question of what came before. This is the precise point where physics runs out and something else begins. The initial conditions of the universe are not predicted by any known theory. The standard model of cosmology takes them as given. Inflation was supposed to erase their signatures, to make them irrelevant to what we observe, to guarantee that no matter what the pre-inflationary universe looked like, the post-inflationary universe would appear smooth, isotropic, and structureless at the largest scales. That was the promise. And the CMB anomalies represent the possibility that the promise was not kept, that inflation smoothed most of the universe, diluted most of the initial conditions below the threshold of detection, but left the very largest modes, the ones closest to the scale of the observable universe itself, still carrying a faint imprint of whatever came before. If that is true, the anomalies are not problems to be solved. They are data from before the beginning. They are the only empirical evidence that will ever exist about the state of reality prior to inflation, about the geometry and topology and initial configuration of the space that eventually became our universe. And we have been treating them as nuisances, as statistical flukes, as instrumental artifacts, has career risks. For 20 years, the anomaly is a window into that question. It may be the only observational window that will ever exist, because the initial conditions of the universe, the pre-inflationary state, the topology of space, the geometry of reality at scales larger than the observable horizon, these are not things we can probe with particle colliders or gravitational wave detectors or galaxy surveys. They leave signatures only in the larger scale modes of the CMB, the modes that are big enough to feel the shape of the container, the modes that have been anomalous since the first measurement and that remain anomalous after 20 years and 2 satellites and 8 data releases. Alluri, Sia, Natale, and 30 other co-authors published a comprehensive review in Classical and Quantum Gravity in 2023, Volume 40, Article number 094001. The paper, titled "Is the Observable Universe Consistent with the Cosmological Principle?", surveyed every known tension with isotropy, from the CMB anomalies to the bulk flow measurements to the cosmic dipole to the fine-structured constant variation reported by Webb and colleagues. Their conclusion was not hedged. Precision cosmology, they wrote, may have outgrown the FLRW paradigm, the mathematical framework that has organized cosmology for a century, the framework built on the assumption that the universe is the same in every direction, may no longer be adequate for the precision of our data. Read that again. 33 physicists, after reviewing the full body of evidence, concluded that the most fundamental mathematical framework in cosmology may be obsolete, not wrong in its approximation, not inaccurate at small scales, but inadequate. The measurements have become so precise that the assumption underlying all of them, the assumption that the universe does not care which direction you look, is now a source of error rather than a simplification. The data has outgrown the model, and nobody knows what the next model looks like, because nobody has ever done cosmology without the cosmological principle. It has been there since the beginning of the field. It is baked into the mathematics at such a fundamental level that replacing it would require not just new equations, but a new conceptual framework for interpreting what measurements of the cosmos mean. You would not just be revising the model, you would be revising the rules for how models are built. That is not fringe. That is a review paper by 33 authors in one of the most respected journals in gravitational physics. And the fact that you have, almost certainly, never heard that sentence, that you have never seen it in a headline or a documentary or a popular science article, should tell you everything you need to know about how cosmology communicates with the public when the news is bad. The calculations have been checked. The quadrupole and octupole share an axis. That axis aligns with the ecliptic. The large angle correlations are absent. The parity is skewed. The dipole does not match. 2 satellites saw it. 8 data releases reproduced it. 4 foreground algorithms confirmed it. 3 independent research groups verified it. Every proposed explanation has failed. The experiment designed to resolve it was cancelled last July. The next one does not launch for 7 years. And the data just sits there in the microwave background, confirmed and unexplained, year after year, the most disturbing measurement in observational cosmology, hiding in plain sight. Somewhere in the oldest light in the universe, there is a direction, a structure, an alignment that should not exist and that cannot be removed by any known physics. It was imprinted on the cosmos before the solar system existed, before the Milky Way existed, before the first star in the observable universe ignited. And it has been there for 13.8 billion years, surviving the expansion of space, the formation of all cosmic structure, and the complete thermal history of the universe, arriving at our instruments as a faint pattern in microwave radiation just a few degrees above absolute zero. Nobody knows what it is. Nobody knows what put it there. Nobody knows if it reflects the shape of the universe, a relic of pre-inflationary physics, or a signature of something even more fundamental about the structure of reality that we do not yet have the language to describe. And the ecliptic alignment, the feature that gives the anomaly its name and its dread, the correlation between the oldest light in existence and the orbital plane of 8 planets around one star, remains unexplained. It may be coincidence, a 1 in 12,000 fluke that just happened to occur in the one universe we can observe. Or it may be the first clue to something we are not yet equipped to understand, something about the relationship between the container and its contents, between the universe and the structures that form within it, between the initial conditions of reality and the specific, local, contingent configuration of matter and gravity that produced a star and a disk of planets, and a species capable of measuring the CMB from one of those planets and noticing that the measurement points back at them. The universe appears to have a structure. It was there before anything we recognize as the universe existed. It is encoded in the faintest signal we can detect, in the first light that ever traveled freely through space, in the afterglow of the moment the cosmos became transparent to itself. And we have known about it for 22 years. 2 satellites confirmed it. Every explanation failed. The field looked away. The experiment was cancelled. And the structure remains, patient and immovable, etched into the background radiation of the sky, like a watermark on reality. You can look at the CMB from any observatory on Earth, and if your instrument is sensitive enough, you will see it. The quadrupole and octupole sharing an axis, the missing correlations at the largest angles, the parity that favors odd over even, the cold spot in Eridanus with no adequate explanation, the hemispherical asymmetry dividing the sky into a louder half and a quieter half, all of it sitting there in the data, confirmed by every instrument that has ever been precise enough to detect it. Not hidden, not subtle, not buried in noise, just unacknowledged by the field that should be most alarmed by it. 20 years from now, a satellite may finally tell us whether the anomaly is in the polarization. If it is, the anomaly is primordial. It was there at the beginning. It is a feature of the universe, not a feature of our measurements. And if it is primordial, it is a message from before the Big Bang, written in the only medium capable of carrying information across 14 billion years of cosmic evolution, the microwave afterglow of the first transparent moment of existence. Whatever put it there did so before time had meaning, before space had contents, before physics had particles to act on, and it left behind a single, measurable, confirmed, undeniable fingerprint that happens to align, for reasons nobody can explain, with the tilt of your world around its star. That is not speculation. That is what the data says. And nobody, not one physicist on this planet, can tell you why.